Just a short speaker introduction. I'm Marc Lemburg. I've been around for ages. I don't even put the time on the slide anymore when I started using Python. I did a lot of work for Python, for CPython especially, and I've also been very engaged in the community. And I have a company, we do Python projects, so if you have anything in that area, then talk to me. But I'm not going to talk about myself. I'm going to talk about a small project I started over Christmas last year. The use case that I had was actually quite a simple thing, but I couldn't find anything really useful in that case, and so I decided to build something on my own. I've been doing talks for many, many years, and I always wanted something that basically makes it easier for me to keep the time and finish on time, which is not easy if you're a speaker. So you want to know something about how far you're into a talk. You want to know about how much time you have left. And if you're giving a talk, then basically you're concentrated on what you want to talk about and not so much on the time. So it has to be visually very, very quick to analyze where you are in the talk, right? So I basically tried to put everything that I ever wanted into this kind of like little project. And I wanted something that is not on a mobile phone, that doesn't turn off during the middle of the talk, that stays on, that's easy to read, works on a battery, should be cheap. Yeah, so those were the criteria I had, and so I looked around and I found this nice little project called Cheap Yellow Display. So if you search for that on the internet, then you'll find a GitHub page that summarizes all the information that someone gathered around these little displays. What it is it's a PCB that has a display, a TFT display, and it has an ESP microcontroller soldered on the back of it. These are very cheap. You can get them starting from €8 per device. And if you wanted to have it fast or not, send it from China, then of course you pay a bit more. It's actually quite powerful, and you can see the device over here. I'm going to pass it around later on during the talk. So it's not too big, it's not too small, you can easily read it. The display is quite bright, so it's exactly the right thing for this kind of project. Next, of course, I wanted to have software run on the device, and well, because this is a Python conference and I like Python, I had a look at MicroPython, which is a project by Daniel George, and it runs a version of Python on microcontrollers. So that was pretty straightforward. Next, I needed something to show graphics, because I didn't want to basically implement everything myself in terms of writing graphics to the display. And then I found a library called LVGL, which is a graphics library that's open source, MIT license. It's very professional. It's being used on a lot of embedded devices. So if you have small devices in your home, for example, that have a display, a touch screen or something, then it's very likely that it's using this LVGL as well. And now, fortunately, there is a port for LVGL to MicroPython, so you can actually program the LVGL library using MicroPython. Now, next thing is you have to find a suitable IDE to work these projects. So I had a look at a few different IDEs that could be used. You see here the Mu editor by Nicholas, which is very nice, but doesn't work that well in this particular case. You have Visual Studio Code, of course, which probably most of you use. I use as well. I tried that, but it's not really usable for this kind of task. The setup is way too complex, and you get lots of weird errors, and you don't want to do this. So I decided to go with Tony IDE, which is, and this is a screenshot of Tony. It's a fairly basic IDE, but it does a very, very good job at interfacing to things like ESP32s. So this is what I used for the development. So next thing is, of course, you need to learn how to use these things, right? MicroPython documentation is very, very good. LVGL documentation is also very good, but only for the C part of it. The extension that you use in MicroPython is actually generated from the LVGL header files, and they have next to no documentation on these things. So you always have to, fiddle around a bit and figure out how to use the Python port of LVGL. What I did is first I tried to use the documentation that's available online, but then I just gave up and then just use an AI chat for that. So that's actually a very good way to do these things, because there are a lot of examples on the internet, and these bots have basically, they read all of these things for us, and so we can just ask them to give us the right information, right? So you don't have to search for them. Now, next thing is you have to put everything on the device. So how does that work? You have, first of all, you have the software, so you need to get MicroPython LVGL onto the device, so you have to flash it, what's called, the firmware onto the device, which sounds difficult, but it actually is not. Getting the display to work is also not very hard. The touchscreen is a bit harder, because there are various different ways of doing these touchscreens. But fortunately, others have already figured all this out, so you just search for display driver for the CUID, and you will get something that works. And battery, you can just use any kind of power bank for that. So for example, on the device I have here, I just used a small power bank, and then it just runs off of the battery. Right, so you have everything put together. Next, you need to put the MicroPython and LVGL onto the device. So how does that work? There are two ways to do this. One is using Tony directly. This does work, but it's a bit fiddly. Much easier is if you have if you just plug in the device into a serial port on your computer using, for example, a USB device, and then you can use the ESP tool .py that you can get to flash the ESP32. And doing that is very easy. So you just give it a file, it flashes it onto the device, it finds the ports and everything by itself. Now, the thing is that, of course, MicroPython and LVGL, they come as source. So typically, you would have to compile these beforehand. And I have a slide at the end of the talk that discusses this a bit. I would very much recommend getting pre-built versions of these things. And if you look for a website by Stefan Scholz, a German who's very much into these things, he has pre-built versions available on the website, and you can just download them and flash those. So that part is easy. Now, how do you develop these things? Of course, you want to basically have the files on your notebook or PC, and then play around with them, and then, of course, to run them, you have to put them on the device somehow. So the way that works is you attach a USB cable, basically the same USB cable you use for flashing the firmware, and then you have to upload each and every file onto the device. If you want to run an application, what happens with MicroPython is that it looks for a file called main.py, and automatically runs that whenever you plug in the power. So that's very easy. So you just write your application based on main.py, and then you just reset the device to start your program. Or you just plug in power. That's basically the same thing. Now, when you iterate and you want to develop the application, of course, you have to re-upload these modules all the time. And then you have to somehow get MicroPython then to understand that you have something new there. So the best way to do that is basically to do a reset. Now, Tony has a feature built in called a soft reset, but that doesn't really work very well for the CUID. So I would always recommend doing a hard reset, which you can do by pressing a button on one of these devices, or you can use the Tony console for that. So you just say import machine, and then you say machine reset, and it does it for you. And then you can just go ahead and test and watch the console for output. The console in Tony will show everything that gets printed to standard out. So in your application, you can, or your small program, you can just use print to print information to the console, and then you see it, and you can see what's happening on your device. There are a few additional development tools that you can use. So one is a simulator, which appears to compile everything to WASM. I haven't actually looked at the details there. But it runs completely in the browser, so it's probably using that kind of approach. It doesn't use PyScript, but compiles directly to WASM for whatever reason. And what I found is that it doesn't support async I/O, so it doesn't have the necessary tooling available to do async work. I don't know why, probably some limitation in that particular port. Other things that you have to do is you have to convert fonts if you want to use fonts on your display and just have the application write the text and then have LVGL convert that to graphics. There are two tools. One is the font converter and another one is the image converter. So for the images, you have to basically boil them down to a specific binary format that is known by LVGL and is highly optimized. And then you can just use the bin files and load them into your application and then have LVGL display things for you. So what if all of this still doesn't get you to basically implement your application or find the right way of how to do it? There are a few ways you can get into this and start working on it. So one is you can have a look at the MicroPython bindings, the notes that they have for LVGL for that. That document I would very much recommend to read because it's actually quite interesting and has many, many subtle details that you would normally not find anywhere else. There's also a forum you can ask, very friendly people there, or you can just ask your AI chat tool. I use Perplexity for these things, and it works great. So there are, of course, some caveats as well. Because this is a microcontroller, managing secrets is hard. There is some logic in the devices that actually allows you to encrypt stuff, but then you have to put the key somewhere, right? So this is not, I haven't really, found a good solution for these things. So best thing that you can do is you just avoid putting secrets in your repos because then they show up on GitHub. But that's about how far it goes, because if someone just takes the device and then just plugs it into the USB, plugs in a USB cable and connects it to a notebook, they can just read whatever is on the flash drive and then just get your secrets that way. Something else that you have to be aware of is connecting to Wi-Fi. It takes a bit longer than usual, so it's not instantaneous. Sometimes it could take like 10 seconds, and just, then just fails, for example. So the typical way to do that is to just retry every now and then. And what I always had troubles with are weird memory and SPI errors. How many of you know what an SPI is? A few. So it's basically like a serial port that connects the ESP32 to the display. So whenever you want to display something or make changes on the display, then it has to go through that particular interface. And this is the thing about the soft reset errors. You often get these SPI errors because you have to reset that port in order to make things work. Another thing is managing memory, but I'll get to that later on. So let's see whether this works. Yes, it does. So this is a little video I did because these devices are small and hard to see. So I'm going to try to do the same thing over here. So this is like the live version of things. This is a demo of the talk timer. It's a 20-second lightning talk, so really short. I just did it because I wanted to show the different things I have. I have this progress bar on the right. I have the background color that changes so that it's easy to see where you are in the talk. You get the number of minutes and seconds that you have left. And then at the end, it starts flashing. So basic stuff, but actually quite useful. And I have a device down there that you can have a look at. It supports both dynamic schedules, like for example this one for doing lightning talks that start when you click on when you select the schedule. And it also supports static ones. So for the conference, for example, you just put in a list and then you have some tuples in there that define what the schedule looks like, and then it automatically starts with the right schedule whenever you turn it on. So if I just turn this on and you see here I still have 50 minutes left to talk and I'm about halfway through, which kind of matches the slide I have here. So that's how it works. Right. Any questions so far? No? Okay. So next few slides are going to give you a bit more insight into how to write these applications. So there are a few hints and tips that I want to give to make it easier for you. One is that you have to make sure that all the UI elements you've defined, so all the objects for LVGL, are kept in module globals. The reason is that they can otherwise get garbage collected, and because the wrapper around LVGL is not, well, how should I put this? It's not too smart, let's put it that way, yeah? So what can happen is that LVGL still thinks that a widget is still around, whereas in Python it's already garbage collected. And then you get strange effects on the display. You also have to have a very good understanding of how you want to start up things, because the startup is initially sequential, just goes to main.py and then runs whatever's in there. But let's say you want to have async code in your application. For example, what I'm using here is I have a clock in there, I have a progress bar, and all of these things are run async. And so you need to know that you have to start with a couple of things that you do sequentially, like, for example, initializing this display. And then you can enter the async loop and then actually start your application. So that's it's important to have. At first, I mixed things up, and then I got weird kind of errors. It's also useful to have lots of small modules, and the reason is just a very practical one. Every time you make a change to a module, you have to re-upload it to the ESP. And this upload actually takes a number of seconds, and if you do that a lot, then it takes a long time. And if you have larger modules, it takes longer, so you want to just upload whatever is needed and basically trim it down to the changes that you made. So this is some code. Basically just an extract of what the talk time actually uses. If you have ever written a desktop application, and this looks very familiar, so basically you just set up the screen, you put some widgets on the screen, you have to put them in certain positions, you have to send fonts. You can, for example, for the progress bar, you can say what the range is and then set the value for the progress bar. You can create buttons, you can have images or icons on those buttons, and you can combine these things. If you look here, then the gear icon actually references the button, so it gets put on the button. And then you can have handlers written in Python, which is nice, and then you can just connect the button, for example, to that handler and have things happen when you click on them. So very basic stuff. A few additional hints. One thing that you should definitely do is you should register what they call a file system for LVGL. And this goes back to the problem with the memory. Ideally, you want LVGL to handle all your memory and basically uploading images to the device, because doing this via MicroPython would then take a lot of RAM, and then you have to garbage collect everything again. And LVGL does this in a smart way. It actually reads stuff in batches and then puts the data on the display. So that's very useful to do. Like I mentioned, the handlers, they tend to just keep working after you've even shut down the event loop. So if you press a button, it will still call the handler, even though you've, for example, in Tony, you ran a break. And so hardware resetting is needed in order to get things working again. So I still have 11 minutes left, which is a whole lot. I'm going to do a few more extra slides. I already mentioned that building from source is maybe not the way you want to do things. And the reason is that it's actually quite complex to do this. First of all, you have to use the SDK for the ESP, and then, of course, you need MicroPython. Those are actually the easy parts. Then you need to use the LVGL library, and you have to have a wrapper for MicroPython. And especially this wrapper part is a bit difficult to get working at the moment, because unfortunately the project that I basically built my stuff on, called LV_MicroPython, it kind of is defunct at the moment. So I don't know what happened. It's very strange. They even took down the issue tracker on that project. And it's been like that since the start of the year, basically. So shortly after I finished my project, they basically stopped working on it. There is a new project called LVGL_MicroPython, and that's actually someone basically taking a new approach to all of this, and it's heavily being worked on. Unfortunately, it's not compatible with the other solutions. So if you want to do something new, then I would suggest to start with the LVGL MicroPython project and not with LV MicroPython, even though getting things working with LV MicroPython is not that hard. And of course, all the chatbots, they still know everything about LV MicroPython and not about LVGL MicroPython, which is always an issue with these chatbots. They keep on, mixing projects and then give you recommendations that work maybe in one project, but not in another. But if you want to compile from source, then LVGL MicroPython is definitely the easier way to get things going. So if you want to compile the other one, LV MicroPython, then you really have to go back like 3 years or so in the code base and then use that version, because at the moment it's not only defunct in the way that there's no maintainers any left, it appears, it's also defunct in that the last maintainer actually removed the support code for the ESP32 for whatever reason. So that doesn't work. So another thing to be careful about is RAM. Now, of course, we have like 32 gigabytes or so on a notebook, right? So RAM is not really much of an issue. For these small devices, it is an issue because the ESP32 only has 520 kilobytes of RAM to use. And once you load MicroPython, you only have 100 kilobyte left. So MicroPython takes away a lot of that RAM, and it's probably there are probably some OS components as well that use some RAM. And it gets worse. If you want to have a display, then you need to load a display driver, and maybe also Wi-Fi support, and then you just have 65 kilobytes left. So, and even if you want to get to this point, you have to be careful with the display driver because you have to use low memory settings in order to make things work. Otherwise, you get memory errors and things just stop working. I also had like a strange experience with these things. This is not really necessarily consistent. So for whatever reason, when the Wi-Fi driver sees a lot of SSIDs in your area, then it uses more RAM versus when you don't have that many SSIDs. So I would suggest if you do something with the display driver, then it's probably better to use even lower memory settings than this. And another thing I experienced, not with this project, but with the this project I did here, a conference badge, which has some images on it, is that it's like I already mentioned, it's a good idea to have LVGL do all of this for you. And the more you use LVGL for this, the better. This will then actually work. You can actually easily put images on the device and show them. Doing this via MicroPython, which I tried first, does not work because of the RAM issue, because you first have to load everything into RAM and then have to offload everything again to LVGL, and there's not enough RAM available for that. So these are more specific things like the display driver setting with low memory. There's a parameter called factor, and you can, if you set that to 8 or 16, then it will actually work. The default setting, I think, is 4 and does not work. So that's why I put this here, and it's a bit hard to figure out. Another trick I used for getting everything working with the wireless, because for the badge, for example, what I'm using is NTP, and I need to get the internet time somehow. So I need the display plus the wireless. What's good about the clock in here is that it actually persists across resets. So, I mean, not removing power, but resets that you do via the machine.reset API. You can first start an application that only takes care of getting the time, and then you do a reset, and then you start the actual application. So you do like a two-phase thing, like a Docker image that first, you do one thing, and then you do another thing, and then you throw away the other stuff. So that's a trick that you can use, and it actually works quite nicely. So I am pretty much on time. So any questions?
Okay, so that was a wonderful talk, Mark. So for the question and answers, so there is a mic. So if anyone is nearby the mic, please use it. So other people who are nearby me, so I can just give you.
Something I forgot to tell you, this small QR code up here, I don't know if you can see it and if it actually works from the distance, but that will get you to the GitHub repo that has the resources for the talk.
Nice. Nice talk. I had a question. If you want to update it, I think at the moment you're doing it by USB. Have you tried maybe using a library to do it over the air, or is it even possible? Like a OTA?
Yes, I know, but I haven't tried it. It might be possible, but given the RAM limitations, it might be a bit difficult. What I think would be possible is to actually download code from the internet or download parameters from the internet and then use them in your application. That should work.
Nice.
Sorry?
The question was to put the QR code slide back.
So sorry. Yes.
I had a quick question that is not software related, but actually more about the actual assembly of the thing. Here.
There you are.
I saw you had these acrylic plates on top. Like, is that part of the display, or is that something you machined yourself as well? They look very nice.
They so what you get is hard to see. I mean, you can come in front and want to see it, but the actual CYD is just this PCB here with the display solid on top, right? And then you can get this plastic kind of casing that has everything that you need to protect it a bit, at least, right? Of course, you can do 3D printing and then do your own case. But these are quite nice to not, to carry it around in your bag and not have them break. So.
Absolutely, I agree. One kind of follow-up question. So did you have to modify them yourself? Like, did you just take some piece of acrylic and then?
No, this is actually the good part about these CYDs. There's absolutely no soldering required. So you can just buy these and then just connect them using a USB cable, and that's it. And even though you don't have to do any soldering, it's very low-level hardware that you're doing.
Really cool project. Thank you for sharing.
First, thank you for your talk. I got me thinking to building my own smartwatch from scratch. Do you think this stack is capable to do it?
It just depends a bit on what you want to put on your smart watch, but it's definitely possible. So, for example, another project I want to do is I use Home Assistant at home for automating everything. And because they have touchscreens, these devices, they're excellent for controlling Home Assistant controlled devices. So what you do is you put the buttons and the scalers and whatever you have on the device, and then it just sends messages to Home Assistant to do stuff.
Cool.
Have you tried with audio data or playing videos on this?
Videos don't work. I can show you, not on this one. I can show you on this one. It's a bit hard to see though, but maybe you can see it. If I press here, then a QR code will load. So I don't know if you can see that. It's very slow, right? So if you want to have a video like that, maybe some comic strip or something. Other than that, it doesn't work. For audio, there is actually a speaker connector on the device, so you can connect a speaker if you like. But as far as I've seen it, you can only do like, beeping sounds, and that's pretty much it.
Okay, so I think that's it. So we are out of time. So let's thank Mark for this wonderful session. Thank you, Mark.
Thank you.